Hello everyone, welcome to this tutorial on system level power analysis with UPM. Really glad to have you all join us on this Monday, the first entirely virtual version of DAC. I'm Nagu, and along with my co-authors, would like to walk you through the Unified Power Model, also known as IEEE Standard 2416, and its use in various design flow scenarios through examples and demonstrations. So to introduce myself, I'm Nagu Dhanwada. I work for IBM based out of the location in Poughkeepsie, New York, and lead a global team involved in the development of power grid, and thermal and reliability tools. In addition to that, I lead the SI2 UPM power modeling project, and along with Jerry Franco, started the IEEE 2416 Power Modeling Standards Committee, which I currently chair. So in this tutorial, our goal is for the participant to get a fair overview of what the UPM/2416 IEEE 2416 standard is about, right? And how it can be used in several aspects of the design flow. I will start with an introduction and cover some amount of detail on what the standard is about, why do we need this, and how the standard was developed, right? And set the stage for the various design personas using whom my co-authors Rhett, Jerry, and David will dive a little deeper into and present some use cases and real-world examples. So in terms of the mission and motivation for the standard, right? Our goal here in developing UPM was to come up with a power modeling standard that truly enables system-level power analysis with very low barriers for adoption. This is really motivated by a need to formally represent power data at the system level. Current standards do not address the formalism of power data. And secondly, being able to represent IP block power data at different levels of abstraction. Existing standards, again, like Liberty, do not address these critical aspects, right? And the other goal was represent power data at a range of PVT points in a single model, which brings in much needed efficiency along with a fair amount of accuracy into system level power analysis. So moving on, right? In terms of how did we go about it, right? Just to give an overview of the operational aspects of this whole work, we are taking an approach of developing a standard which stands a good chance for industry adoption, right? Through how we structure the work. So the core technology comes in from member companies. In this case, some of the core technologies came in from IBM. And within SI2, we work on taking this contribution and making it acceptable for general industry consumption, right? This is done through various extensions to the standard itself, defining linkages to other standards, and coming up with a formal specification. And this specification is contributed through IEEE 2416. And within the IEEE 2416 working groups, we take contributions from entities like SI2 and other member companies, and finally, release that to the industry, right? Now, all the while doing this, we iterate on making sure that this spec is feasible and realizable by working very closely with universities in developing demonstrations and prototype implementations, right? So the whole concept here is, not just come up with a standard and publish a document of the standard, but really along with that published standard, provide prototypes and proof of concepts and demos and everything, which gives confidence to the people adopting the standard that the standard is actually realizable. So that is really our goal here. Now, just to give a very small overview of the big picture timeline of when we started and where we are now, this slide shows a timeline for the standard development process from its inception back in 2014 through the IEEE Standards Association sponsored Low Power Coordinating Committee activity, and through a lot of intermediate milestones. The standard was formally released as the IEEE 2416-2019 V1 back in June of 2019. It was announced as a part of DAC last year. So that's really took us 4.5 years to get here, but I think it's got some significant work went into making this possible. Yeah. Now, in terms of who all were involved, right? We had the slide just shows a list of all the companies who were involved in the development of the standard. So here is a list of, in fact, all the companies who were involved in development as well as final voting to approve the standard. And as you can see, there's a representation across, semiconductor companies, cloud companies, systems companies, EDA companies, and the whole spectrum, right? So this has been a standard which has representation from all parts of the industry. Yeah. So now I would like to switch gears a little bit. In the next few slides, I would like to get into the details of the what, why, and how of the standard in order to give a little better sense of what we're talking about, right? So what is the standard trying to address, right? So three aspects really, right? So one is the IP and component abstraction. The second part is process voltage and temperature independent modeling. And the third main aspect is model continuity and interoperability through formalism of data and interfaces, right? Both within design flows as well as across abstraction levels. So I'll get into details of some of these pieces, but that is really what the standard at its heart is trying to address. Yeah. Now, why do we need to address these, right? So first of all, really efficiency and accuracy are paramount for modeling energy and power impacts at the system level and beyond, right? So the whole notion of efficiency is delivered in terms of abstraction capabilities, right? In order to facilitate large-scale system simulations that are power aware, right? And at the same time, delivering accuracy in these models, which are used in these system level simulations, are also very valuable so that we can avoid significant over design and not have to build in large margins, right? So you clearly see that currently there is no standard way to represent power data across a range of PVT points. There is no standard way again to represent power data consistently across multiple design levels, as well as no standard way of providing power data to 1801 system level power models, right? The whole notion of PVT independent modeling significantly helps in the efficiency part of it, which I mentioned, right? It reduces the effort for multi-corner characterization. It does not it kind of precludes the need for inaccurate interpolation and extrapolation, and the whole notion of design continuity, right? I mean, and across design levels, across abstraction levels, is also needed, and it's actually facilitated through some of the contributor-based modeling concepts, which we'll introduce later in the presentation, right? So now to get into the how part of it, right? Before we get into a little bit more details on the how part of it, we would like to address some of the needs, to really introduce the notion of what we call as the power contributors, right? So this forms basis for the PVT independent modeling aspects of the UPM standard, right? So if you really think about it, contributors to power dissipation are mostly separate, right? They can be separated very clearly, and they encapsulate different device physics, right? So examples of these are, let's say, the channel or gate leaking width of devices, the switching of a capacitance, and the crossover current, for example. So these are all, you can actually separate the power dissipation into components like these, right? And that's the inherent ability of how to model power, right? So these separable components of power are called power contributors, right? So the total power is a sum of these separable components, and basically each contributor behaves the same in different cells, thus giving us the ability to share contributors amongst multiple cells, right? Uh, so this concept of contributors, which we'll elaborate a little bit more on, have been proven and successfully used on several generations of microprocessor designs within IBM. Yeah. Now, the little bit onto the how part of it, right? So think of power contributors as nothing but power proxies, right? So in a traditional power model, we have power data is actually stored in the model, right? But here, the power data is not stored in the model. Instead, the contributors to power are stored in the model, right? So think of structural aspects of the design being stored rather than evaluating the power and storing the power in the design, right? So examples of these power proxies are a leakage power proxy, which is essentially, let's say, leaking transistor width, right? And that is the one part which is actually stored in the model itself. And from that, leakage can be calculated using the W effective, the effective leaking transistor width, which is stored in the model, and using certain parameters provided by the user at the time of evaluation. And similarly, you can also think of an energy proxy, which models your dynamic power, where you essentially store equivalent capacitance in the model and not the dynamic power in the model. So essentially, you're storing the equivalent capacitance. And for you to get to energy and dynamic power, you will use the C effective, which is stored in the model, and then provide the voltage, temperature, and state, which could be provided by the user at the time of evaluation. Yeah. So now, a little bit on how this kind of the contributors and hence PVT late binding improves power flows. If you think about it, in a conventional library power flow, characterization is done for every cell at every PVT point of interest, right? So that is, the PVT conditions are applied during power model generation itself, right? Which leads to us requiring a large number of circuit simulations, and the fact that the power analysis is specific to a particular PVT, uh, right? I mean, that is really what is done. If you need analysis needing to be done at a different PVT point, then you would have to do some, interpolation and extrapolation to actually accomplish that, right? So, so that is essentially in a conventional library power flow, right? Where the power model build step itself applies the PVT, which you can think of it as the early binding. Now contrast that to a contributor library based power flow where there is a single PVT independent power model is generated from the power model build step that works across all corners, resulting in minimal library characterization effort with no simulation needed. And the right? So the generation step itself in a contributor based flow is essentially uh, 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 some sort of structural analysis of the library and the design to come up with the PVT independent model. And when you are actually calculating power, you apply the PVT points, which kind of leads you to this lazy evaluation / late binding kind of a concept, right? Which makes it very easy for you to for you to literally do analysis at any PVT point, right? So that's in essentially the kind of late binding which is provided in the contributor-based flows, right? Um, so now, so even though the a little bit on how the UPM relates to UPF and the existing 1801 standards, right? So even though the 1801 standard added power state modeling capabilities in the terms of the power expressions, intentionally, the data representation for power was not addressed in that standard, right? So what 2416 accomplishes when interfacing with 1801, you could think of it that 2416 formalizes the semantics for power abstraction of complex IP and models PVT independence, and it kind of formalizes how the data is stored. And the 1801 model literally captures the power states and power domains. It captures the logic expressions determined during the current power state. It affects the parameters. So it captures the whole logic and transitions and everything. And the power expression data or the power data is formalized by the 2416 standard. So you can think of the interaction between 1801 and 2416 in that manner, right? So little more, right? So the UPM standard itself, right, is set up to be a multi-level model that can serve up power data throughout the entire SOC flow, right? Right from 1801 system level power estimation all the way to gate level power estimation, right? So in this multi-level structure, at the highest level are applications that use the 1801 models, right? The system level portion of a multi-level UPM model will serve up static power and dynamic power numbers through the system level data and the associated power expressions, right? And at the lowest level of this multi-level structure would be the contributor level, where the data is stored as contributors, and the contributor evaluator converts this data to static power per state and energy per event to be provided to Liberty applications, right? Now, in addition to serving up data to the Liberty applications, there could also be new EDA applications that could directly consume the contributor level data, right? Now, in the middle is the gate level or direct level of the multi-level model, where we could have Liberty-like data that is served up via power expressions to the 1801, or directly the static power per state and energy per event can be served up for Liberty applications itself, right? So this slide kind of illustrates the multi-level structure of UPM itself, right? So now, in terms of the persistent representation, we use a XML schema. So this is, think of it like a a self-checking model where the model structure is described in an XSD schema, and there's a formalization of the model contents, and the schema enables automatic model structure validation itself, right? Now, getting on to the overall model architecture itself, right? You saw in the slide, we show the 2416 library on one side and the power tool, which is actually using the 2416 library. The general architecture, again, as I mentioned a little bit earlier, is a multi-level architecture, which provides backward compatibility with existing gate level models, right? This architecture also enables a single model with multiple levels and multiple representations to be used at various phases in the design flow, right? The gate level provides the storage of data for backward compatibility with legacy modeling approaches, right? And the power and energy data returned from this level are identical to that provided by Liberty, essentially, right? So these are the static power per mode and energy per event information, right? The system level again provides for interoperability with the 1801 component power state models, and the output from the level is consistent with the 1801 power expression attribute of the add power state command, which expects to receive static power and dynamic power for a defined state, right? Several inputs need to be added to provide this power data, including the operating frequency and others, depending on how this 1801 model is configured, right? Now, if we need a voltage independent system level power model, the data may be represented directly by expressions, right? And of course, at the lowest level are contributors, which can go through a contributor evaluator, and that can also feed back into legacy Liberty-like applications as well, as I had mentioned a few slides back. Yeah. Now, a little bit on the contributor evaluator. The contributor evaluator is an expression or a set of expressions that evaluate a contributor using specified parameter values in order to return power or energy, right? The UPM specification does not mandate any particular implementation, and it can be anything from a circuit simulator to a simplified set of equations that are evaluated in line to compute the power and energy values, right? So here you see, the input are the contributors, and there are also a process parameters as well as environmental conditions, which are input to the contributor evaluator, and the output you see energy per event and leakage power per state. Yeah. Now, the next slide, we show a simple example of a contributor defined in XML. Here you see there's a name to the contributor, there's a type associated with the contributor, and you can think of the static power contributor to be a single 4-terminal equivalent transistor from which leaking currents are calculated according to the leakage current equations that are appropriate for a target technology. Yeah. So now I show a quick snippet of a more complete UPM model. There's a system level model with expressions. Jerry will touch on this in our RISC-V rocket examples more, but what you kind of see here, there are a bunch of cell parameters which come from the workload, and there are some expression parameters which come from characterization, and then the dynamic power expression itself is actually shown in the model here. Yeah. So switching gears a little bit, right? I just want to quickly highlight the use of it in a generic system to silicon power aware design flow, right? So in essence, you can think of a generic design flow to consist of 3 phases, right? One is our electronic system level, there's an RTL design stage, and there's an implementation stage, right? Each phase, to varying degrees, contains a design, analysis, optimization, verification tasks, and each phase relies upon the availability of accurate and efficient models, and each phase produces power data that is passed down or forward to subsequent phases, right? In order to realize this flow, multiple power aware technologies are required. You need various tools, like simulators, synthesizers, etc., languages, formats, and models also, right? Here we see some representative power aware activities on the right hand side, or tasks that are relevant and typically undertaken during each design stage, right? And for these activities to be effective, power data and power sensitivities to the various modes, stimulus, etc., are really required, right? So clearly, in the overall flow as it stands, there is a lack of high-level power modeling capabilities, lack of standards for high-level modeling, and there are lack of models that can actually work easily across this ESL, RTL, and implementation stages, right? So for us to really deploy a comprehensive power flow, right, which encompasses ESL, the whole system level, through implementation, we need models for each design stage, right? So today, while very, we have very good modeling capabilities, which exist at the lower levels, at the higher levels, there really are no standards, right? And execution of this ideal power aware design flow is limited by model availability, right? Now, here's where UPM comes in order to bridge this gap through an efficient multi-level model architecture and provide several efficiencies like contributor models while ensuring backward compatibility. So in order to set the stage for the rest of the tutorial, I want to introduce the different personas in a design flow who would benefit from the use of 2416. Right? So there are 2 categories of users you can think of, right? One will be the model creator, an example of which is an IP developer. And then there are model consumers who are system architects and also SOC designers who are using various pieces of IP to come up with their system/SOC design, right? Now, from an IP developer perspective, there is currently he or she would have to generate their models, right? Their power, models for various PVT points to make sure it works across different foundries, across different use cases and everything else, right? And consuming several simulations and everything. Now with 2416, an IP developer should be able to, generate a single UPM/2416 model, give it out to the users, and the users will basically configure it under the, conditions in which they want to use that IP block, right? So that's one example, and Rhett will continue to elaborate on, and give more details on an IP developer's perspective. Then from a model consumer standpoint, SOC architects typically deal with early spreadsheets, and there is no continuity in the design flow which they have. And use of UPM in their use context is something which you know, they derive value from the whole model continuity across abstraction levels and within design flows aspect, which we highlighted earlier, right? Jerry Frankel will highlight a system/SOC architect's perspective, and David Rachkoff will highlight the SOC designer's perspective and how UPM will benefit SOC designers. And Professor Davis will also, you know, touch on the tool provider or EDA tool provider on how UPM will benefit them. Yeah. With that, I would like to hand it over to Red Davis to continue and get us into the next stage of the tutorial. Thank you.
Hello, I'm Rhett Davis, and I'm going to present now UPM from the perspective of the IP provider. And I'm going to do that by taking on her persona. So for the next 12 slides, call me Izzy, the IP provider. In reality, I'm a professor at NC State. I'm also technical and education advisor to SI2, and I've been a member of the IEEE P2416 working group since it was created. So now, as an IP provider, my goal is to provide a verified library of cores with a balance of power, performance, and area that my customers want. Now, my customers want power models, and they expect me to provide them, or enough detail of the design so that they can create them themselves. Now, I'd rather provide the model to protect my IP in general. Now, I also want to target my cores for as many EDA tools and foundries as possible, because doing so increases my customer base. But it can also potentially multiply my effort of having to retune that core for many different tools and many different processes, and generating enough data for every single point that my customers want. So that's a problem. It could potentially multiply my effort. So hopefully, as the UPM standard matures, then more EDA providers will support UPM, and so that solves one of the problems. And in the few slides down, I will also show you how you can use UPM to target a different foundry. So first of all, let me illustrate the core that I'm providing. So let's imagine that I'm providing a CPU core similar to the rocket ship from UC Berkeley and the Free Chips Foundation, as illustrated here. So this, like this rocket tile, for example, the rocket tile, which is designed out of standard cells, it's designed out of memory macros, and it's got a processor, it's got caches, it's got a high-speed bus interface. So this is the core that I am providing. Now, how do I estimate power for this core? So on this slide, I'm showing a state-of-the-art power characterization flow. I create benchmarks, which I will then put into a Verilog RTL simulation of my core to generate activity data. And then I can feed that activity data in the form of VCD files into a power estimation tool or flow that reads in my standard cell and memory liberty files and generates power reports, which I can then parse into a spreadsheet where I collect all my different power data. Now, there's a number of problems with this flow. First of all, it can take hours to run and use gigabytes of storage. And I need to potentially do it for every single PVT point, process voltage and temperature point, that my customers want, which is an awful lot of effort and an awful lot of expense for me. Second, once I have generated this data, I need to be able to maintain consistency and traceability for every single point in my spreadsheet so that I can debug any mispredictions. And that's also an awful lot of expense. And third, what do I do if I've got missing files? I don't have the PVT point that my customers want, or if I want to target a new process, how can I proceed? So let's start with a look at how UPM will help me to just manage my data. So even if I only have one PVT point, I have elements that help me track the units and conditions for that PVD point, and then annotate the dynamic and static power for every single benchmark that I have, which are called states in UPM, just the same as they are in the UPF IEEE 1801 standard for power intent. And then as I start generating more and more samples, I can bring my power tables into UPM as well. So I'm showing here an expanded view of one of the static power states with a table for static power parameterized in terms of voltage and temperature as indices. So UPM also supports multi-dimensional arrays with as many indices as I want. And I've listed up here a number of the typical indices that we see for both dynamic power tables and static power tables. So in the UPM working group, we often call these top-down models because they are generated with a top-level view of the entire hierarchy. And they more or less represent the typical way in which we manage power data today. So great. So UPM helps me to manage my data more easily. But what if I can't generate the data in the first place because I've got missing Liberty files, or I'm trying to target a new process? What do I do then? So in order to predict power in those cases, this is where we need what we call a bottom-up model in the UPM working group, or a PVT independent model. We need to take what we know about the structure of the design and capture it in a way that allows us to easily extrapolate it to new PVT points and new processes. So now, to be the most useful, I want to replace my top-down model with this bottom-up model, which means I need it to be equally accurate to the top-down model. And I can accomplish this by capturing the structure of the design using these static and dynamic contributors that Nagu mentioned earlier. So he introduced them, but let me take now some time to go into a bit more detail about each one, starting with the static power contributors. So leakage current varies quite a lot over a range of process voltage and temperature, but it can be predicted fairly easily with node voltages, which don't vary nearly as much. So if I want to predict power accurately for a complex design, I simply have to decompose it into a set of stacks, which are what we call the static power contributors that exist in the design, and then pick one transistor in that stack and then characterize it over the full range of process voltage and temperature to come up with expressions for, expressions for the node voltages in that stack. And once I have those expressions, then I can use those expressions with any process voltage temperature point that I like to predict power very accurately, as I've shown here. I do that by applying those node voltages to the same SPICE models equations that were used to characterize the node voltages in the first place, as well as the static currents. So it's got the same accuracy as SPICE. However, it's much, much faster because I don't need to do any of the Newton-Raphson iterations that I did for the SPICE simulations. And also, just the number of contributors is not that large. There's a finite number of stacks in the design. And so as long as I compute the power for each one of those, I've got a pretty good estimate. Now, for the sake of time, I'm going to leave it there, but I'm giving you a reference to one of the papers that we published that describes this process in much more detail at ISQED last year. So here I'm giving you a brief image of how this static power contributor looks in a UPM standard cell. I've got the characterized node voltage expression down here at the bottom, and in the cell definition, I've got the reference to that contributor model. Now you'll notice that that the dynamic energy, well, actually, before I say that, let me mention that the same structure here is going to work for standard cells as well as a memory macro. There's really no difference. It's just a matter of picking the stacks that you would have in the memory macro. So there'll usually be a different set of contributors for the memory than there would be for the standard cells. Also, I'm noting here that I'm still using a dynamic energy top-down style table for the dynamic power of this cell. And that's because the dynamic energy contributors are much more useful for cores, for a high-level core level than they are for the standard cell. So let me segue now into talking about dynamic energy contributors in a bit more detail. So unlike static power, dynamic energy varies much more with activity than it does with process and temperature. But it can be accurately predicted with events using this expression that I've got up here at the top. So if I want to predict power very accurately for a complex design, I first need to decompose it into a number of events and then characterize the amount of switched capacitance represented by C sub j in this expression for each one of those events. And then to estimate power, I simply have to count the number of events n sub j that occur over a certain number of cycles, capital N, and then multiply them together to get an expression for the dynamic power. So for the demo that you're going to see later, we did this for the rocket tile from the RISC-V rocket tile from UC Berkeley, as I'm showing in this table down here. For every single instruction, we characterize the amount of dynamic power. And as you can see, over all of those instructions, we got a variation of around a factor of 2.5 in that dynamic power, which is typical. So I'd also like to thank Alan Baker from ANSYS, who's a member of our working group, who also did all this power characterization for us using their tool, Power Artist. I'd also like to reference the creators of the tool Microprobe from IBM, which was the tool that we used to generate all of the workloads for each one of these instructions so that we could characterize the power. Now, it's important to note here that nothing about UPM helps me to do this decomposition of my system into these events for dynamic contributors, or the static power contributors, the stacks for that matter. But what UPM does allow us to do is allow us to automate this entire process of characterization and automation once I've made the decision about what that decomposition will be. So now on this slide, I'm illustrating how we characterized one of these energy contributors, namely the data cache fill event. So we created a benchmark that allowed us to force fill events if we increased the number of loop iterations. And that allowed us to then generate power or sample the power both with and without cache fills, and then use the equation from the previous slide to reverse out what the dynamic energy was for that cache fill event. So to do that, we had to solve a number of technical problems. One thing we had to do was search through the activity to find windows in which the execution was not being interrupted to the debug controller. We also had to find windows where there were no instruction cache fill events, as I'm kind of showing here and here. And then we had to make sure that we had a non-trivial significant number of data cache fill events, as I'm illustrating down there at the bottom. So then once I've gone to all that effort, UPM gives me a nice format to capture this result in a way that's precise and easy to communicate. So once I'm done with all this, I have a complete UPM model that allows me to perform system level power analysis over a wide range of process voltage and temperature points using any kind of dynamic voltage and frequency scaling that I want. I can use this much more simplified flow that I've got down here at the bottom. So it's a much smaller data, much faster. I simply take my events and I feed them into a UPM power analysis tool that takes that UPM file and allows me to generate a system level power report like the one I'm illustrating here. So I will leave you with this image from the demo that you're going to see in a couple of minutes, which shows how power is evolving over time with different PVT and DVFS scenarios. So with that, now let's pause, and I will take off my Izzy hat, and I'll put on the hat of Eddie, the EDA provider. So let's talk in the next 6 slides about UPM from the EDA provider's standpoint. So as an EDA provider, my goal is to provide tools that enable successful state-of-the-art designs in current and future technologies to as many users as possible. Now, my customers want full system power modeling capability in my tools, and they expect me to develop it for them. But they don't want to share their data with me, which creates a problem for me, because I don't really want to develop this unless I know for certain that it's going to solve their problems. Now, as I develop this capability, I also want the tools that I develop to satisfy a number of criteria. I want them to be fast, efficient, and accurate. I want them to use the same or similar model so that I don't have to keep developing code for different formats for different tools or different levels of abstraction. And I'd like to make sure that these tools, these capabilities stick around for a long time. And like I said before, I want to be sure that they are going to solve my customers' problems. So as I talked about earlier, as the IP provider, UPM models can be made very fast and efficient and accurate. And you can use the same model for the system level all the way down to the standard cell. So UPM checks off the first 2 criteria. And again, the efforts of standardization through IEEE 2416 hopefully ensure that it's going to be around for a long time. But what about this last point? How do I know that this is going to solve my customers' problems? So let me take, let me actually show you 4 potential applications for UPM, which we think represent things that will be in high demand as the standard matures. So the first application is to automate this process of getting final power numbers for every single block in a system before its release. This is typically done today by a manual process of going around to every designer and extorting a power number out of them and to put in a spreadsheet, which is typically called the roll-up. Jerry Franco is going to talk more about this in a few minutes when he goes into the system architects portion of this talk. This process is a pain point for many companies, but it's the state-of-the-art way for doing system verification and also planning for the next generation of designs. So UPM would really be ideal for the development of product lifecycle management tools to help manage and automate this process of system roll-ups. So that's application number 1. Application 2 is simply to provide fast system level power calculators. So all system architects want this capability. And as evidence of this claim, I will point you to MacPat, which is what the vast majority of system architects use, despite its well-documented incorrectness. And what I've shown here on this slide are some images from one of my favorite papers by Andreas Gerstlauer's group at UT Austin, where he's taking samples of power from real hardware and using machine learning algorithms to tune MAC-PAT models into something that's more correct. Now, I think it would be much simpler and much more useful to use machine learning algorithms with samples of power data to create a more correct model in UPM and then provide that to users instead. And if we do, then there's every reason to believe, due to the popularity of MAC-PAT, that these tools would be equally popular. So that's the second application. The third is pathfinding, which is the term for physically aware virtual prototyping for the purpose of technology selection. This is especially useful for 3D IC design, for 3D IC chip stacking. And I've included a reference to one of our papers down here at the bottom, where we were using transaction level power models tied in a flow with a thermal solver to explore the impact of different floor planning decisions in a chip stack. And we found, is kind of shown in these first two images here, how much faster we were reaching thermal runaway if we chose to floor plan cores on top of each other rather than distributed in the stack. We also, as shown in this third plot over here, were able to explore the impact of throttling the processor to be slower once we started approaching thermal runaway. So this was all done with a set of homegrown tools that were not particularly reliable. But with UPM and coupled with UPF, we can start to build tools that are going to do this in a much more reliable way, and start to make things like floor plan optimization that takes chip stacking and DVFS into account. So building on this idea of combining floor planning with thermal solvers, the last application that I want to talk about is temperature reliability co-optimization, which refers to this idea that you can trade off lifetime and performance in a multi-core chip by creative scheduling of the workloads to adjust the temperature. This works because different mechanisms for transistor degradation become dominant at different temperatures. So, and I've included some images from one of my favorite papers on this topic, which was actually published here at DAC 6 years ago. So again, we see that this work uses MAC-PAT despite its inaccuracies. But it's reasonable to think that that if we were to use UPM and UPF to do this much more accurately, that designers are going to want this capability and to design their systems. So that was my last new UPM-enabled capability, but I suspect that there's many others that are out there just waiting to be implemented and developed as this standard matures. So in summary, UPM enables full system power modeling capability in a way that's fast, efficient, and accurate. It gives me power model continuity from the system block level all the way down to the standard cell or contributor, and it gives me a way to interact with my customers and enables a wide range of long expected tools. So with that, I am going to hand it over to Jerry Franco, who will present UPM from the system architect's perspective.
Thanks, Rhett. Hello, I'm Jerry Franco from SI2, and today I'll be speaking as a system architect and describing how UPM helps me do my job. I'm currently Director of Open Standards at SI2, where we developed UPM. I'm also Vice Chair of the IEEE P2416 Working Group, where we formally standardized UPM as IEEE 2416. As a system architect, I have several goals regarding throughput and performance, cost, schedules, power, and reliability, and have specific targets for power consumption and junction temperature. I'm also concerned with managing my risk as I pursue those goals. So to do that, I need to have early estimates for energy, power, and junction temperature to guide me in my design decisions. It could be a career limiting move if I don't find out where I am relative to my goals until late in my project. I need early, accurate information. In pursuing these goals, I'll be designing with IP from multiple sources, various external IP vendors, as well as internal IP design groups. Each of these different groups is likely to provide their data in different formats, single values, tables, graphs, or expressions, if they have it, but many don't. If they do have it, the delivery mechanisms are likely to vary too, from data sheets to spreadsheets, proprietary formats, or even gate-level netlists that I would need to simulate. Finally, sometimes when my IP provider can't or won't provide the data I need, then I'll need to build my own models. As a systems guy, I really don't want to do that, but I will if I have to. So to achieve my goals, I have several wants and needs. Chief among these are early, reliable system-level power and thermal estimates. I want to see at the block level power consumption values and junction temperatures. I need to know the total energy consumed at my worst case temperature, but I likely won't know a priori what that worst case temperature will be. I'd like my models to support successive refinement flow. By successive refinement, I mean that I'm willing to work with estimated or first order models early in my design, but want mechanisms by which I can easily refine or replace my model with more detailed data when it becomes available. This is especially the case with regards to temperature. I also want an efficient mechanism for rolling up power estimates for my entire system, all components, all functions, analog and digital. And I don't want to use a spreadsheet. They're simply too error prone and require too much effort to create and support. I need something better. Fortunately, UPM was designed to meet my needs as a system architect. Here are some of the key features. First, multiple data representations are available. Scalars, multidimensional tables, not just two-dimensional tables, but n-dimensional. Expressions, and a new construct, contributors, which are PVT-independent power proxies. But whatever the representation, static and dynamic power are represented separately. The PVT independence means for me that I only need a single model to represent whatever corners I need to analyze. And importantly, UPM was designed from the ground up to be interoperable. It's now an industry standard, IEEE 2416. It's built on standard languages, XML and Verilog-A, and it's designed to interoperate with other standards such as UPF, IEEE 1801. UPM supports a couple of different use models as shown here. On the left is a post-simulation time flow, and on the right is a simulation runtime flow. The flow on the left, the post-sim time run flow, is working today and will be demonstrated in a few moments. This general flow is well known and well used for gate-level power analysis. In that case, the design is simulated and a VCD trace is captured for all signal transitions. This is, I'm sure, familiar to most all of you. UPM can be used in the same manner, with the big difference being that all bit-level signal transitions are neither needed nor captured. Instead, event counts are captured for specific model parameters, and power is calculated based upon the UPM and the event counts. The flow on the right, a simulation runtime flow, does not require a separate power tool such as PowerCalc, but instead requires a UPF 3.0 compatible simulator and communicates with UPM through the 1801/2416 API. Let's look in a little more detail at the different data representations. Scalars are simple and make model creation simple. It's most useful for quick first cuts, such as I might use in my earliest design activities. Tables are well known for power modeling, and UPM not only supports them, but extends them from the usual 2 dimensions to n dimensions as needed. Tables are often used in top-down characterized models. Expressions may be arbitrarily complex and can be used for both static and dynamic power. Expressions are particularly useful to me as an architect, since I can often analytically model the power effects of different architectures without necessarily first implementing those different architectures. Contributor-based models are of great interest to me due to their PVT independence. I can estimate the PVT effects on leakage with expressions, but the contributors will provide the best accuracy. And then finally, multi-level models are supported. This is unique to UPM. These models can be used in low-level VCD power analyses, such as for gate-level power analysis. And the same model can also be used in abstract system-level analyses. These models have a single data store, but can return power data at different abstraction levels, hence the multi-level moniker. Now, let's take a look at a couple of different system-level models. Here's one example of a system model provided by an external IP provider. This is an expression-based model populated with a datasheet equation. I should point out, this is a standard chip. It's a TI battery charger chip. And this model, you can see the UPM on the right represents exactly what's in the datasheet. So this model has a single state, 1 power expression, and 10 different power parameters. Here's another example. This is a snippet of a RISC-V processor UPM. This model is an energy per instruction model, simple and elegant. In an application, we would count the number of times an instruction is executed. Here we show the loads and stores, and then multiply that number by the characterized energy for that instruction. The rich set of UPM semantics enables this straightforward representation of the processor's power characteristics. Now, note the green expression. This shows that this is a voltage and frequency independent model. This means that this model can be used to calculate power consumption at any voltage and any frequency. Now, we've seen a couple of different system-level model examples. Next, let's look at several use cases or target applications for those models. Here is a clear motivating example for the need for system-level models shown on the previous slides. This is generally how full system results are collected or rolled up today. But this is a big challenge. Setting up, debugging, and maintaining this spreadsheet for multiple scenarios, a full system roll-up of at least 20 different devices, static and dynamic power, analog and digital, 3+ scenarios, actually many scenarios. As an architect, I need a more effective power roll-up than this. I need accurate, reliable results without requiring too much modeling effort to make efficient trade-offs. Spreadsheets can be accurate, but they're often unreliable in that, and they require way too much support, too much effort to support. I need something better. And here is a better approach, using UPM power models for each chiplet. This is an actual design produced by Z-Glue, a Silicon Valley startup that develops chiplet-based systems and ICs using a smart interposer technology. So you can see this example includes 7 different chiplets. And on the right, in the power graph, produced by our tool, PowerCalc, it shows 6 different scenarios. So you can see here that UPM models enable this kind of analysis and roll-up, as a single model can be easily used across these multiple scenarios. And the fact that power data can be modeled with any of the multiple representations provides great flexibility in model creation. Some of these models use multiple states, some use a single state, some use expressions, some use scalars, but all 7 chiplets are modeled using UPM. Now, this next example speaks to where both system design and modeling technology are headed. Getting good system-level power estimates is necessary, but in the end, it is not sufficient because good thermal estimates, thermal analyses are also necessary. And this is another area in which UPM provides great value. But let's look at this example a little more because it's very illustrative. This example comes from research at Northwestern University, where using academic tools such as McPat, they analyzed the power, thermal, and throughput characteristics of this 3D stack. You can see there's a processor on top and 5 DRAMs stacked below. What they found is that the highest overall throughput occurred at a frequency less than the maximum operating frequency. Basically, by running at less than the maximum allowable frequency, they were able to minimize the maximum junction temperature, which in turn reduced leakage, which required fewer refresh cycles. And with fewer refreshes needed, overall throughput was maximized. This is a significant counterintuitive result. But results like this are hard to reproduce because the work was done using old academic tools such as McPat, which are notoriously difficult to adjust for other designs or situations. So, to properly do this analysis with minimum risk and cost, accurate and correct tools and modeling methods are needed, which is where UPM comes in. In just a moment, I will run a power analysis of a dual-core RISC-V SoC, as shown here. Each of the rocket tiles will be modeled with a single top-down energy per instruction model. You saw a snippet of that model earlier. The model is parameterized by the counts of each executed instruction. The other 3 blocks, the system bus, the memory bus, and the TL to AXI interface, are each modeled with an individual top-down model as well. The demonstration scenario is as shown here. Basically, a thermally aware DVFS system in which the operating voltage, frequency, and junction temperatures vary with each time slice. 4 different workloads are used in this analysis, which computes power for each of the 10 unique scenarios. We'll vary the frequency from 100 megahertz to 1 gigahertz, the supply voltage from 0.9 of a volt to 1.1 volts, and junction temperatures from 35 to 110 degrees C. Now, you might want to think about how you do all this with conventional tools or a spreadsheet. So the demo will run our tool called UPM PowerCalc, which is a UPM-compatible power analysis tool developed at SI2 to be a demonstration vehicle for UPM. What you'll see in this demo is a single power analysis run for a DVFS system utilizing an energy per instruction power model of the RISC-V. A single power model will be used for all the various voltage, frequency, and temperature conditions. Okay, now I'm going to switch from presentations to demonstrations using my virtual machine and kick off PowerCalc. So here I invoke PowerCalc from the command line using a command file here, tutorial6.uc. So let's take a look at the contents of that command file so that you can see what we're doing here with PowerCalc. So first we specify the design files, dual-core SoC.v. That's the Verilog system-level description of the dual-core chip that we showed you earlier. Here we point to a scenario file that contains the DVFS information that we showed you as well earlier. We'll look at that more in a moment. Here we point to the models, the UPM models that are being used to analyze this chip for power, and then finally a few various PowerCalc tool commands. Now here is the scenario file that contains the DVFS information. First, we show here that we're assigning a workload called boot to I1 and I2. Later in the simulation, we'll show or we'll assign other workloads, but initially they're both booting. And you can see the voltages, the frequencies, and the temperatures at which they're operating initially. Here you see the parameters that the model is parameterized with. And within the parentheses for each, you see the counts of the various events. Here we show 1,223 iCache fills. And here the power calc is completed. So let's take a look at these results. And let's also, while we do that, show the DVFS scenario. So here we see power calc has calculated the power consumption of this dual core SoC in 10 different time slices as illustrated here. So in the first one here, we see that both are running a boot sequence and they're both consuming quite a bit of power. But after the first time slice, instance I1 begins to execute a floating point dominated workload, while instance I2 is idling. So you see there's a fair amount of power consumption here for I1, not so much for I2. I should point out that some of the shading on these colors indicates that the darker ones are dynamic power, the lighter ones are static power. So we're computing static and dynamic power for each of these instances. And you can see that the power consumption varies substantially depending on what's happening with workload, voltage, frequency, and temperature. That's not surprising. We know that that's what happens. What's remarkable here is that power calc using a single model is calculating all that. And just for kind of a final measure of interest here, while instance I1 is calculating here and I2 is idling, they swap roles way out here in the 10th time slice. So I1 is idling, the frequency drops to 100 megahertz. The voltage drops as well, while I2 is still cranking away. And we see that happening. We see both the dynamic power varying as well as the static power varying as it's temperature sensitive. So now, in short, you have seen here a full system level power analysis based on UPMs for a dual core RISC-V based SoC running multiple workloads under DVFS. So in summary, you've seen that UPM can model all parts of a system. This includes a RISC-V processor to battery chargers to accelerometers and pretty much anything in between. UPM can be used in a successive refinement flow. Simple models created early when you have limited data can be easily replaced with more sophisticated models when that data becomes available. It should be pretty clear that UPM robustly replaces spreadsheet-based analysis and rollups, saving time and effort and increasing the reliability of the results. And the bottom line of all this is that UPM makes life easier for system architects. And I like that.
Thank you, Jerry, and welcome everybody. I would like to cover UPM from the point of view of system designer. My name is David Rajkov. I'm the CEO and founder of Trace Systems. I have worked on power-related tools and methodologies since starting my career in LSI Logic in '99. My interests span power and power modeling. I'm happy to announce that we are launching the first commercial tool to generate and use UPM IEEE 2416 models. In my presentation, I'm going to talk about UPM from the point of view of SoC designer. I'm going to explain how bottom-up UPM can be generated for libraries. I'm going to give you a brief demo of Trace Systems power meter tool that utilizes and generates UPM models. And I'm going to conclude my presentation. As an SoC designer, I'm constrained in my ability to estimate early SoC power by the lack of complete libraries. I need to estimate power for various PVT corners for which I don't have libraries yet. Additionally, while I may have some libraries for some of the IPs, for others, I may not even have any libraries yet. For example, it's typical that standard cell libraries may be completed earlier, while memories, being more complex IPs, are not available yet. I would like to use libraries from previous technology and previous generation of the design to estimate my power. I also need to exchange power data. I need to get information from the architect, what the assumptions were, what his power numbers were, what they look like. And also when I implement my block, I would like to send that data back to the architect so that he can validate that the power is still meeting the desired targets. Or alternatively, I would like to send that data to another user in the flow where they can do power analysis. UPM helps me solve all of these problems. UPM as a model captures proxy information. This proxy information allows for power calculations to be done later with the appropriate power model. What this means is that now with the UPM library, I can estimate power at any PVT point I like with the model which I just received. It also allows me to map between technologies. I can reuse libraries from previous technologies or different technology or the previous generation of the IP and map that to my current technology and perform power analysis early on. Most importantly, it allows me to estimate power at any PVT point. This allows me to do what-if analysis, to do trade-offs, and to make sure I'm meeting my power targets. It also allows me to capture my power analysis data into file format and hand that off. I can hand that off to the architect, where they can validate that the targets are met, or I can hand that off to various users in the flow, such as system engineers and so on. Most importantly, that data handoff happens in a common standard format. I no longer send data in spreadsheets, in PowerPoints, or by email. All this happens in a standard format that any tool can read. We already covered power contributors. Power contributors allow us to bind process models much later in the flow, which in turn allow us to perform estimation of power to any PVT point we like. While working on this tutorial, we encountered the same problem that any SoC designer will encounter in their normal work. We had standard cell libraries, which were generated much early, and they were not using the latest models. So we would have liked to be able to update libraries with the latest models. For the memories, we did not have them in our target technology. We were able to generate them in a different technology and then map to the technology we were targeting. How would we have done this had we not have UPM? Previously, we would take the libraries, fudge all the power numbers in them, as difficult as it actually is, and generate new libraries and use those for power analysis. That fudging is obviously not very accurate. With UPM, we don't have to do that. We just use the latest process model and we can get power estimates at the actual PVT point we like that's based off of the actual process model. As I just mentioned, we needed to generate bottom-up UPM models for our standard cell libraries. For these libraries, I did have Liberty files, but not for my power corners, and I also had a SPICE netlist. We applied our power meter flow, which is typically applied to in cases like this where we have Liberty files, some kind of Liberty file, and some kind of SPICE netlist. We use these to guide what the tools should be, what kind of characterization to perform, what kind of simulations to perform, and they work as is. There are no additional tool inputs. As a result, the tool will generate IEEE 2416 compliant UPM power model. For the more complex IP like memories, we also needed to generate bottom-up UPM models. These were slightly different. For these, we did have Liberty and Spice Netlist, but they were at different technology. They were not at our target technology. For this, we applied the same process. First we generated bottom-up UPM power model, and then the next step was transistor mapping. Transistor mapping we obtained from our expert, Professor Red Davis. And with that transistor mapping, we were able to generate bottom-up UPM model for the memory in a flow that's very similar to a simple standard cell. There are most different uses of this mapping flow. One is, as I mentioned in our case, we use it to map between technologies. You can use it to generate libraries at brand new VT, for example, and still get power analysis done without having to actually generate any of the Spice netlists. Another way to generate bottom-up UPM power models is for complex blocks. In these blocks, I will have UPM for all of the IPs. I will have UPM for the standard cell, I will have UPM for memories, and for everything else. With those IP UPM models, I can generate bottom-up UPM model for the entire block. This UPM model can be vector-based or vectorless, and still be contributor-based. This UPM model, I can hand off to the power architect to validate that the targets are met, or I can hand it off to different users in the flow. Most important to note is that the resulting UPM model is still PVT independent. The power analysis flow, which uses UPM models, is very similar to the classic power analysis flow. We still load all the design data. We still load all the models, and just in this case, they're IEEE 2416 UPM models. The only additional step is that we have to provide the process model at this point. Providing the process model at this point allows us to perform the late technology binding, which guarantees that we're using the latest and greatest process model. And most importantly, it allows us to target any PVT point for our power analysis. I will now demo UPM with PowerMeter. PowerMeter is our power analysis platform, which we have developed at Trace Systems. One of the important features of that platform is its ability to generate and use IEEE 2416 compliant UPM power models. PowerMeter is a power analysis platform that spans from gates to system level. And today our focus is going to be on gate level UPM generation. So what you're going to see is me generating bottom-up UPM for a standard cell. You're going to see me mapping bottom-up UPM for a memory between technologies. You're going to see me estimating power at any PVT point using UPM data. And you're going to see me importing top-down UPM, which I received from my architect, into PowerMeter. In this demo, we are going to generate a couple of bottom-up UPM power models. As a first step, we're going to generate UPM models for standard cells. We are starting at a point where we have loaded Liberty files into PowerMeter and are ready to proceed with model generation. Just to show you what the standard cell library looks like, as I mentioned, we're limited in what power coordinates we have. In our particular case, we had 5 corners in total. We had 2 fast, 2 slow, and 1 typical corner. Fast is high voltage, low temperature, low voltage, high temperature. And on the slow side, the highest temperature we had was 0 degrees C. So definitely we did not have enough power corners to perform full power analysis. To do that, we're going to generate UPM power models. I'm going to switch to the command line tool now, and I'm going to run the command that is used to generate the UPM power models. What you're going to see happening in the command window, it's going to tell us which cells it's working on, and on the right side, we're going to see all the data being loaded. Here is the data for the inverter. If you remember the pictures for what UPM looks like, we have two states, and for each of the states, the two transistors are leaking differently. One is contributing gate leakage, the other one is contributing subthreshold leakage, and in the reverse state, they switch, and then NFET will be leaking subthreshold, and PFET will be leaking gate leakage. This is what the actual data looks like. Looking at the whole library, we can actually see what devices are being used in this library. We have 9 devices which are used in different configurations, of 9 NFET devices which are used in different configurations, and 5 PFET devices used in different configurations for both the inverter and the NAND 2 cell. Generating the actual UPM power model involves running another command, which will read all this data from our database and create the actual file in the directory I'm working in. In a moment, the file will be generated, and I can show you its contents. You saw some examples of that earlier. This is how it looks like. The model starts with unit definitions. Here's the power contributor definitions, which basically define the terminal voltages on each of the power contributors, each of the transistors. And here begins the cell definition, which defines pins, and most importantly, it defines power in terms of power contributors. And this is all it took to generate UPM model for my standard cells. We saw how we can generate bottom-up UPM models for standard cells. For these, we generated the UPM model from scratch. The other option we have to generate UPM models is for cases where we already have the UPM models for the IP at different technology, and we want to map to our target technology. This is what we had to do in our case when we use the memories compiled by OpenRAM compiler. If you haven't seen OpenRAM compiler, please go check it out. It's fully open source. It's developed by UC Santa Cruz. So we generated memories at 45 nanometer technology, and for them we generated UPM models. Our target technology, however, was 50 nanometer. So to generate bottom-up UPM models for the 50 nanometer technology, we are going to apply technology mapping, and I'm going to show you how to do that. In our case, here's what the memory content looks like with all the various transistors. As you can see, memories have a very rich set of transistors being used. We have 5 different memory types which we used in our test case. To map the memories we use to our target technologies, this is what we're going to do. We're going to open the project. We're going to point to the technology we want to use. We're going to point to the technology version we want to use. We're going to do, naturally, when mapping technologies, we need to map layer stack. We need to map what the various sources are. And this is where our power contributor mapping window appears. We have the source transistor type, and we have the target transistor type. These are pre-populated with values which we have received from Professor Red Davis, mapping one transistor type to a different transistor type. You can see we have the full list, and we're just going to say update. The tool is going to take it, and it will map the memories device types to the device types we use in 50 nanometer. There you go. You saw the change. Now we have memories which have been mapped from our source original technology of 45 nanometer to our target technology of 15 nanometers, and we have the UPM, and we have the data to generate UPM models for those. Next, I'm going to show you how we can use UPM to estimate power at different TVT points. As I have been mentioning all along, one of the biggest benefits of UPM is the ability to estimate power and leakage at any process voltage and temperature point, even for ones for which we have not generated models. This is how it looks in action. I'm going to come and create a case. In my technology, I have defined the extreme fast corner to be with value of 1, extreme slow corner -1, and typical corner will be value of 0. So when defining process, if I say process of 1, typical RC, I'm going to look at 125C I'm looking at duration of 1 nanosecond, and I'm going to look at nominal voltage. Remember, we did not have library for that corner to estimate power. I can also estimate power at another corner. I can say, I want to do slightly off a fast corner estimation and see how my power is going to look like there. And I also want to do a little bit lower temperature. I don't have to do 125. Say hypothetically, my device works at 110. And again, I want to see at lower temperature how that looks. So what if I wanted to do slow corner? And remember, I did not have high temperature liberty for the slow corner. And yet UPM would allow me to do that. And not only I'm going to do slow corner, I'm going to do slightly off a fast corner, off a slow corner, excuse me, and say I want to do 0.8, typical RC. But because it's slow corner, I may want to do higher voltage, 0.85. What if I want to do something else? Say I want to do fast corner, slightly off a fast. I want to do 110. But most importantly, I want to do very low voltage. I want to do low voltage operation at 0.7. How would that look like? What is my power going to look like? This will appear here. As you can see, now with all of this, we can produce power at any process voltage and temperature point, and we can see where our highest power is, where our lowest power is. All this with one single power model. Now moving on to the last step of our demonstration, I'm going to show you how we can import UPM power model. In this case, I'm going to be working with the UPM that my architect used to estimate his power early on. I'm going to navigate to my project, and I'm just going to say that I want to import UPM. I have different ways that I can import the designs into Power Meter. In this case, I'm going to choose UPM. I'm going to point to the UPM that my architect used, the same exact UPM that they used, and I'm just going to import it. And in the background, you're going to see all the 4 cells which are generated: the rocket tile, system bus, the memory bus, and the bridge design. Looking into the design, I can see that it has imported all its components. It has imported all its parameters, which come from the model. Some are constants, some are variable parameters. It has additionally imported all the power definition, the equation that's used to estimate power. And this is all it took for me to import UPM into Power Meter. In summary, UPM allows you to estimate power for any PVT point you like with a single library. You don't have to create libraries anytime you want to change your power corner. It also allows you to exchange data with other tools and users in a standard tool-readable format. I have also shown you a demo of the first production-ready power analysis tool to both generate and use UPM IEEE 2416 compliant models. Back to you, Nagu.
Thank you for the very nice demo, David. Before we wrap up, I want to spend a minute going through the impact of UPM 2416 adoption to power-aware design. So just to highlight some of the value adds which we see, so some of them are, to start with, there's a cost savings perspective that comes in because of accuracy improvements that leads to removal of conservatism and power estimates. There is schedule savings that comes about through the detailed insight into sources of power consumption, right? That comes from adopting some of the concepts in UPM. That will essentially reduce hardware debug and model to hardware correlation times. There is significant compute resource savings that happens through a very efficient multi-corner power analysis. Once there are tools that end-to-end adopt UPM, there will be significant productivity by having a unified environment right from your spreadsheet and high-level modeling through to sign-off, right? Now to wrap it up, the UPM IEEE 2416 standard takes a significant step towards formalizing power data representation across levels of abstraction. The version 1 of the standard was released last DAC, as I had mentioned, and there are tools and demos that go along with the standard, which highlight the practical feasibility of the standard. We did see the whole RISC-V example, which Rhett, Jerry, and David walked us through. And there are early versions of tools from SI2 as well as Trade Systems, which are available to generate and consume UPM models. And we saw some snippets of them during the demo. And last but not the least, participation in the IEEE 2416 group and or the SI2 UPM working group is highly encouraged for interesting folks. We really ask you to join us in taking this to the next level. With that, we have listed some web resources for additional information and some contacts here. So feel free to get in touch with any of us and getting in touch with me and Jerry if anyone wants to join either the SI2 UPM working group or the IEEE 2416 working group. Thank you. Till next time, signing off now.